Okay, welcome to the European Non-Associative Algebra seminar. Today is July 31, 2023, and we have a talk by Şehmus Fındık from Çukurova University, Turkey, and he's going to talk on symmetric polynomials in certain non-commutative algebras. Please.
Okay, thank you very much for this opportunity, first of all. So my talk is about some certain non-commutative algebras, including Lie algebras, Leibniz algebras, and so on. So the main idea of this work is constructing some invariant theoretical but slightly easier structure as an algebra and finding the generators of this algebra. So invariant theory, okay, maybe it starts before 1900, but after Hilbert's problems, which revealed in 1900, it became more popular. So let's start by a polynomial. So let K, X, and be the polynomials in n-commuting variables, and G be a subgroup of the general linear group. Then a polynomial is called G invariant if under all actions or under the action of all elements of G, F is preserved. So such Fs consist of a set, and this is an algebra, which is called the algebra of G invariants. So David Hilbert suggested 23 unsolved problems in the International Congress of Mathematics. And we focus on the 14th Hilbert problem, which is in the following. So if we focus on the algebra of G invariance in the polynomial case in n variables, then is this algebra finitely generated as an algebra? So in 1994 or 1959, in some sources it is written like 1958, but the exact paper was in this way, and it's in 1959, it doesn't matter. So Nagata gave a counterexample showing that this algebra of invariance cannot be finitely generated in all subgroups of a general linear group. But there are some partial significant answers, one of which is given by Emil Noether in 1915 or 16. It also depends on the sources you read, that for finite groups, for all finite groups of general linear group, this algebra is finitely generated. And in particular, if we handle the subgroup G as Sn, the permutations, so we visualize each permutation as a matrix n by n, then this algebra is also finitely generated, and the explicit generators of this algebra is given in this way. So here E1 up to En, they are called the elementary symmetric polynomials, and they are algebraically independent. So of course there are more sets of generators. For example, when you have x1 up to xn being f1, and f2 is x1 square up to xn square, and so on up to fn. This is also going to be a set of generators, but it is not algebraically independent. So now we check whether what we can do for the Lie algebras. And among the Lie algebras, we have the free metabelian Lie algebras. So a Lie algebra is a vector space with a bilinear operation, which is called the commutator, satisfying CQ symmetry and the Jacobi identity. And these two, okay, in skew symmetry, x squared is 0 or xy is equal to minus yx. These two are equivalent when the characteristics of the field is not 2. And the metabelian identity is given in this way. You have the commutators of commutators, which is 0. Or you can create such an algebra in this way. You have a free object in the variety of the algebras, and this algebra is divided by the derivative of its derivative, which is the commutator of commutator ideal, and you again get the free metabelian algebra. And a symmetric polynomial, this algebra is going to be defined in the same way. So basically, when you go back, so you see here a polynomial is called symmetric when it is preserved under all changes of its generators. So the same definition holds also here. A polynomial P in Fn is going to be a Lie polynomial that's preserved under all actions of each permutation. So when you observe in the free metabelian Lie algebra, in fact, in any metabelian algebra, Lie algebra, you have the following. When you have an element W coming from the commutator ideal, and the add of X, which is the adjoint operator acting from right side. Sorry, is there a question, or let me see, sorry. Or may I answer in the end, or?
Yes, there is a question in the chat. Well, if you wish, you can answer now.
Yeah, sure. Do you have a nice example of metabelian Lie algebra? Yes, there is. So when you, okay, I shouldn't, okay. So when you have, for example, the matrices with entries from a ring, okay, this should be upright triangular, of course. The multiplication is defined in the following. So you have a matrix A multiplied B is equal to AB minus BA, where the multiplication between them is the usual multiplication. So the first commutator vanishes the diagonal, and then when you multiply again, it becomes 0. So let me go on. So adjoint operator here acts as a multiplication, or I mean, as a multiplication of the commutator from right side. So this is W commutator X and then commutator Y. And then you make use of the Jacobi identity and then skew symmetry to get that adjoint operator on the right side is commutative when you have W is coming from the commutator ideal. So a basis was given by Bakhtin in his book, Identical Relations in Lie Algebras. It was published twice, one in 1985 and then 1987 in English. And here we have a very nice looking basis. When you pay attention here, when we multiply two elements, considering this part being as a W, then you get an element inside F prime, which is the commutator ideal, and all other elements when you write them in the left normed type, then all the elements after the third one are commuting. So you see this commuting structure gives F prime being a KXN model structure from right side. The same thing might be on the left side too, but there are some minuses. So maybe it's more convenient to use this multiplication from the right side. So working in free metabelian Lie algebra has some advantages. So the first advantage is that Fn to the Sn is a Lie subalgebra. So when it is a subalgebra, the natural questions comes up to be, do you have generators? What are the automorphisms and so on? And then by metabelian identity again, we have KXN to the Sn module structure. And Dransky showed that the Lie algebra Fn to the Sn, of course, this is the special case. He showed for characteristic 0, Sn can be replaced by all G finite. It's finitely generated. And Dransky and his colleagues show that Fn to the Sn is a finitely generated KXN, the KXN to the Sn model. Okay, not finitely generated as a Lie algebra, but it is finitely generated as KXN to the Sn model. So we can work only with finite number of generators in here. So the first attempt was in 2019 by a colleague of mine, and we showed that an element coming from F2 to the S2 in general looks like this way, and it is generated by this infinite set. And this set is a minimal set, but we didn't up to one more year we couldn't generalize this for any n, and then by the help of Dransky we did something more to generalize everything for any n greater than or equal to 3. But for fn to the Sn, when n is greater than 3, it was more convenient to work in the read product. So this read product is the usual read product coming from Schmelkin, and in this case you have L prime embedded into this one. In fact, all L, L, not L, F. Fn is embedded into this read product. I didn't write in detail, but it can be found in the paper. And here, each element of this type, so here Pijn, we write this one for the adjoint operator. So every y, for example, y1 stands for adjoint of y1, which means we multiply from right side with x1. So we can consider Pij as a polynomial in commuting variables. And in the read product, you have this one. So why do we work in the read product? Because you see here, in this case, the read product is the free module generated by n elements as a polynomial algebra, as a module of polynomial algebra. So after working in here, we give an implicit description of fn prime to the Sn. It is given by this. So here you have the generating set, and in the generating set you have Hij's, which are defined in the read product, and the inverse images of them under the embedding psi gives you the generators. So here in the read product, what we have is in this way, and this is the general form of it. But of course, maybe in explicitly written for small n, we can visualize it. But before it, maybe the idea of proof can be given a little bit. So the main idea depends on this one. So you have a polynomial algebra in n variable, another n variable, and so on. So you have many ones, and Sn acts simultaneously on Xn and all other n sets. But when you restrict it to two sets, for example, here U and Xn, because you see here Un are elements in the read product and Xn are the polynomial variables, then you get this one. But in our read product, since Ui times Uj becomes 0 because of the metabelian identity, you get that this reduces to this theorem. So in this theorem, everything can be written more easily, and as an illustration, maybe we can give an example. So, for example, when you have an element of length 4 in terms of commutators, and in particular H24 to the 4. So how to compute it? So first of all, H24 to the 4 is a very long expression. Instead, we work as a coefficient of U1 only. So its coefficient looks like this one. When you expand it, you get such an expression. And for U2, U3, U4, because it is inside a module generated by U1, U2, U3, U4. And we have all these things. And then after some arrangements, you get such elements. So for example, here, U2 x1 minus U1 x2, when you have its inverse image, it stands for x2 commutator x1, and here x4 commutator x1, and all other elements in here are the adjoint operators. Because when you go back, please, here, for example, xi xj stands for ui xj minus uj xi times all other elements here. So when you go back to here, you get the adjoint operators. So in the end, what you get as a generator is in this way. So you have only one of the elements in here. So in the case in generators in the case of a two generating set, f2 prime to the s2 is generated by as a kx2 x1 x2 to the s2 module, generated by only one element here. So this one element is x2 times x1 commutator x2 minus x1. In fact, this can be observed also in the finding what was given in 2019. Let me go back to this slide. Sorry. So in the case of rank 2, you see here you have such elements here. So you can also work on these generators in here. So when you have this one, in fact, what's on the right side is a polynomial, and this polynomial can be divided by x1 minus x2. And when you have the multiplier of it, it is a symmetric polynomial in k x1 x2 to the s2, which is x1 plus x2 and x1 x2. So these are the generators of these are the elementary symmetric polynomials indeed. So when you go to rank 3, you have 3 generators here. In fact, this is 3 choose 2. This is the number of generators here, but we are not saying that these are the free generators. And for any n, we have g of ij's, where I is less than j, and they vary from n1 to n, and it's also n choose 2. But again, they are not algebraically independent. So these are the generators for rank 3. And for rank 4, we have 6 generators, which are looking in this way. Yeah. So this is what was done for the free metabelian Lie algebras and their symmetric polynomials. The algebra of symmetric polynomials are generated by all these elements. So in the Poisson case, free metabelian Poisson algebras are also worked in 2019 by Zhang and his colleagues. So a Poisson algebra is, in fact, having 2 multiplications. One is the commutator, and the other one is associative and commutative. And if we look for a free Poisson algebra, maybe it can be obtained by a free Lie algebra, because when you have a Lie algebra in your hand, you have also its basis. And the polynomial algebra generated by this basis, which is an infinite number of generators, gives you a Poisson algebra. But when you have the multiplication, both of the multiplications are being 0, then the Poisson algebra P is called abelian. And when you have the extension of an abelian Poisson algebra with another one, it's called metabelian. And the symmetric polynomial also defined in the same way. So these are some identities held in Pn, but pay attention that there are some restrictions on these dot multiplications which are associative and the commutative, but there is no any restriction of length of the commutators. Once this dot appears in it, you can have at most length 3, but when you have only commutators, the only restriction is the metabelian identity. So this means that you may multiply A by B as a commutator, and then one more B, one more B, one more B. Okay, you are not allowed to multiply 2 elements in the commutator ideal only, but you can have the commutator elements very long. So Zhang et al. Here, there are 3 writers here. They gave a very nice looking basis. So when you check for this basis, it is in 4 pieces. So this union of this 4 B1 up to B4, it gives you the basis of the free metabelian Poisson algebra. But the first one looks very like to the free metabelian algebra. So the free metabelian algebra in this respect can be embedded into the Poisson, the free metabelian Poisson algebra. So when you look for the symmetric polynomials in Pn, it is first we have to check whether all these vector spaces are invariant under the action of Sn, and it seems that it is, and then it is sufficient to work independently in everyone. But KB1 is exactly the free metabelian algebra which was discussed in the previous part, and the second one, B2, let's go back to B2. So you see here, B2 consists of the elements of length 2 and length 3 coming from the polynomial algebra. So working with the symmetric polynomials in KB2 as a vector space is exactly working with the polynomial ones, but the polynomials of length 2 and length 3 only. But B3 and B4 are the new arguments here. So you see KB1 to the Sn is already known, which is just done before. And the next part is KB2, which is also a result of the polynomial one. So we are looking for only a basis elements. We have 5 base elements in here. So each symmetric polynomial in KB2 Sn can be written this way. And the KB3 to the Sn, okay, by working the identities given above, we can, this result was given. So we have only one element here as a basis. And also in KB4, depending on the rank, we have 2 types of elements. So when rank is 2, we have only a single element in the basis. But when n is greater than or equal to 3, we have 2 basis elements in the symmetric polynomial, okay, as a vector space. Because when you multiply 2 elements inside here, it doesn't make it's not closed. Okay, it is closed, but it gives you 0, because when you go back to these vector spaces here, so you see when you multiply 2 elements of such elements, it becomes 0 because of the identities given here. It is same for B2, B3, and B4. The only lucky one is B1. Yeah. So when you visualize the elements in here, so P2 to the S2 is spent on these elements here. So G stands for the symmetric polynomial of length 1, which is only x1 plus x2, nothing more. And G1, 2, which is adapted from the metabelian Lie algebra. And the P's are the new elements, which are the consequences of Poisson algebra here. And in the case of 3 elements, of course, we have more elements in here. Here, pay attention that these Y's are standing for the adjoint operator. Okay, G12, G13, and G23 are the Lie elements here, and all others are non-Lie elements. So for 4, again, we have 6 generators of Lie type, and Lie type. Again, of course, these are the same generators coming from the Lie case, and the Poisson type elements are here. So these are the basis elements, of course, but these are the generators. So in the Leibniz case, again, we work with the free metabelian Leibniz algebra. So a Leibniz algebra is a vector space with bilinear operation as a commutator, but this commutator is not same as the commutator of the Lie algebra, because in the Lie case, we have skew symmetry and the Jacobi identity, but here we do not have both of them. Okay, you can have, but in this case, you will get this particular case, which is the Lie one. So in this respect, we can say that the Leibniz algebra is a generalization of the algebra. And when you work with the metabelian Leibniz algebra, free metabelian Leibniz algebra, a very nice looking basis was given by Drensky. I wrote it somewhere, but maybe here. Yeah, Drensky and Cattaneo. So this is the base. These are not the basis. These are only the properties, and here is the basis. Sorry. So here you see we do not have non-equal here because you see x1 times x1 is not 0 anymore here in the Leibniz case. So the commutator ideal of Ln is the free metabelian Leibniz algebra. Of the free metabelian Leibniz algebra is a free right K-Rn module here. So Rn means that you multiply, you have the commutator from right side acting exactly as the adjoint operator in the case of Lie. So let's go back. It was written here, I think. Yeah. So R of Z means that you multiply from, these two are same things. So xy times rz means x times I times z here. So this is the main theorem in the Leibniz case. It's a little bit very complicated, in fact, not a little bit, but the visualization for small ranks, we have these ones. So L2 prime to the S2. Okay, we are working in the commutator ideals because the linear elements are already known, and they are all coming from the polynomial case. And here, I put this one in the first place because when you give it a skew symmetry, for example, you have the same generator as the Lie one, and all others are 0 in the Lie algebras. You see x1, x2, minus x1, x2 becomes 0, x1, x1 is 0, and so on in the Lie case. Okay, you see this was the generator of the free metabelian Lie algebra in rank 2. And we have additional ranks in here in order to get a compatible result. So in rank 3 also we have more elements in here. And the Grassmann analog. So here we have all associative algebras satisfying this identity. Z1 commutator, Z2 commutator, Z3, which means this one in associative case, and the free object of rank 3 is coming from here, and we work with this one. So you see here, we work only with rank 1, rank 2, rank 3, but the basis here is a little bit more interesting. This basis was given, we can see this basis in the book by Drensky, maybe here is the name of his book. And here, what's on the left side is commuting, and what's on the right side is not commuting, but because of the identity, just this slide you see here, when you change the position of this two or any of two elements, you have a minus in front of it. So it allows you to rearrange the indices of xi's here. So we fix I1 greater than or equal to up to I2C and so on. Of course, we have an even number of elements here. And what's on the left is commuting, but not always. So you see in rank 2 and rank 3, because of these identities, you see this is 0. So it means that x2, x3, or x3, x1. So this is a misprint, I think, here. And they are all zeros, which means that when you have rank 2 and rank 3, what's on the left side can be changed. So they are having the kx2, the polynomial algebra, and kx3 module structure. But in the case of n greater than or equal to 4, we do not have the same thing, and we cannot move on with the polynomial inheritance. So we work only with f3 and f2 prime. So you see f2 prime is turns to be the kx2 model generated by one element, and f3 prime is generated by 3 elements given in here. And the symmetric polynomials are in this way. So the symmetric polynomials in rank 2 is generated by this element as kx2 s2 left module. So here you multiply from left side. And in the case of 3, you have 3 generators in here. And again, we are not saying that these are algebraically independent. But of course, you cannot multiply, because once you multiply them, you get 0, because you see here you have at least one common element. For example, x2, x1 multiplied, okay, by this one, it will be 0 because of the identity. And x2, x1 multiplied by this one, you have a common element. Because why am I saying this? Because of, okay, let me come back to this identity, because this is the key role. See it. For example, if Z2 and Z4 are the same things, you can carry Z2 up to here because of this identity, and you get 0, of course, because the commutator of x by x is 0 always because of this definition. So what can I say here? I can say that, okay, the multiplications are 0, but okay, maybe they are algebraically independent, but I didn't view it as in this way. Sorry, up to now. Okay, I did it. Sorry, I did it. So this is pretty generated. So this is many years that, okay. So the idea of this one is that, first of all, you have a general element in F3 prime, and then if it's a symmetric polynomial, it should be in this way. So it is FABC times a symmetric polynomial coming from xkx3 to the S3, and then this is the general form. After that, we are trying to reduce the number of generators. So these are some reductions here. So by means of these reductions, you can reduce everything in terms of, okay, here's sigma 2, sigma 1, sigma 3 are the elementary symmetric polynomials. And VC means x1 to this to the power c up to some x3 to the c, and this is also symmetric. So multiplying by symmetric polynomials, everything can be reduced to these 3 elements, which are stated in the theorem here. So this was the main idea here. So generic matrix analog. So we handle here 2 matrices with entries coming from the polynomial algebra. And it is generated by 6 elements here, x1, x2, x3, y1, y2, y3. And these traceless matrices, okay, you have 2 matrices here. And the unital associative algebra W is generated by x and y. And its Lie subalgebra is denoted by L, which is also generated by x and y. Of course, here L is the free algebra in the variety of SL to K. So there are some results here. In 1978, there is a presentation of this algebra. Of course, here x square and y square are the scalar matrices here. Because of this, of course, these are 0, but this is the only presentation relation. And you see here TUV given by trace of x squared times I2, which is the identity matrix of size 2 by 2. So it is also 2 times x squared. So from also here, we can say that x squared, y squared, and xy plus yx are all scalar matrices. And the interesting thing is that the center of this algebra, the W, is generated by these 3 elements. And it is a free KTUV module, which is the center of W. With these 4 free generators, you have I, X, Y, and the commutator of XY, which is XY minus YX. So also for the Lie subalgebra, we have 3 generators, 3 free generators, which are in the Lie form, in fact, because, for example, the first one is 1/2 times X commutator Y, X commutator Y commutator X, and here you have 1/2 times X commutator Y commutator Y, and this is X commutator Y, and so on. So there are more results in the paper. Okay, explicit forms of the actions of VTUV multiplied from left and right side here. Okay, maybe it's not 1/2, but twice. I really don't know exactly. We can check. So here we have the first one. Okay, W to the S2, which is the symmetric polynomials of W. So it is going to be defined in the following. So because in S2 you have only non-trivial element, the transposition 1, 2, you have the changes of these two generators. So this is freely generated by these 4 elements. This is the first result. And the second result is for the Lie algebra. So L prime to the S2 is also generated by this, where A is this element and Y is this element. Okay, these are also the generators of the element in the algebra. So associative analog. So this is also the free metabelian associative algebra, but here we restrict our consideration to only rank 2 because for rank n greater than or equal to 3 is still work by Dransky and his colleagues. Here we have, first of all, F as a free algebra, free associative algebra, but non-commuting variables. And A prime stands for its commutator ideal, and you have the square of this element. So this means that this is the metabelian identity for the associative case. And now we work with this F, and we have a nice looking basis which was given by Bakhturin. Okay, there are results in these 2 books which are given in below here. So we can change the positions of x's and y's here, and also from that side. So this is the result for F2 to the S2, and we have 1, 2, 3, 4, 5, 6 generators in this algebra as an algebra generated by, because in all other cases, in the Leibniz case, in the Poisson case, in the Lie case, we work with the Kxn to the Sn module, but here we have the algebraic structure here. And as a summary, I wanted to see what happens in the case of rank 2. So in the case of rank 2, the free metabelian Lie algebra is generated by this single element. In the Poisson case, this single element is together with all these elements are generators. And for L2 prime to the S2, this element coincides with which element? Maybe this element, no. This element, yeah. And all others are the other elements. And when you divide the Leibniz algebra by its annihilator, you get the Lie case, and in this case, all these elements become 0. And in the Grassmann case, you see a very nice looking and similar looking element here. But the difference is that here, Y is the adjoint operator. So you have the commutator multiplication here, but you have only the associative multiplication here. And the free metabelian associative algebra, you have these elements here. But you see here, again, you have a very similar element. And in the generic matrix case, you have this structure, but one should be very careful about here that x squared minus y squared here doesn't mean x minus 1 times x plus 1. So we cannot say that these are the same elements here. So what can be done next? So first of all, what is the application of these polynomials or the algebras of these polynomials is the first thing that I really want to know. And the second is that one should determine the automorphism group of these algebras for any f in any variety. And also what can be done for the same results with algebras over the fields of prime characteristics. And this was the end of my talk. Thank you very much for listening to me.
Thank you very much. Other questions? Okay, no questions. So let me thank the speaker again.
Thank you very much, Professor.
Thank you.
So how can I share my slides with you? With the
I think just send the PDF by email to one of the organizers.
Okay.
And the video will be shared on YouTube.
Okay.
So thanks again for your talk. And
Thank you very much, Professor, for this opportunity. And thank you for every audience here.
yeah, thank you for the participants again, and we'll meet next week. Let's see.